Hey, my name is Matthew. Welcome back. We're going to be doing some mathematical statistics, looking at standard deviation and standard error. Alright, so first we'll cover standard deviation, then standard error. Then we'll go over a bit of an example showing the relationship between standard deviation and standard error when we're looking at the mean of a set of samples. Alright, so standard deviation is a measure of how spread out data points are around the mean of the data. Given a random variable x, the standard deviation is given by sigma is equal to the square root of the variance of the random variable x. So sigma squared is the variance. Now, a quick reminder, the variance is equal to the expected value of the squared random variable minus the square of the expected value of the random variable. Okay, here's just a quick illustration to show you, to give you a better idea of what the standard deviation means. So here we have two different samples, one of them from a normal distribution with a standard deviation of 5, and one from a normal distribution with a standard deviation of 2. So you can see that most of the data is lying, or rather, most of the data points are lying between one standard deviation of the mean, which is 0 in this case. And here again, you can see that the data is clustered around the mean and, for the most part, within the standard deviation. It's important to point out that there are two different types of standard deviation. We can talk about the population standard deviation, and we can talk about the sample standard deviation. So, for example, with this data, we're showing the population standard deviation, which means that these data points were sampled from a distribution where the distribution has a standard deviation of 5. If we were to calculate the standard deviation of this sample, it would be different from 5. We'd expect it to be close to 5, maybe a little bit below or a little bit above, but it would not likely be exactly 5 because the sample standard deviation is an approximation of the population standard deviation. Alright, so what is standard error? So given any statistic, as an example, the mean of a sample, the standard error is defined to be the standard deviation of that statistic. Suppose that we have xi, our random variables following distribution d. The notation for that is this. So we have some distribution d, and xi is sampled from that distribution. Then an independent sample of size n would be the n independent random variables x1, x2, up to xn, all distributed from the, or all sampled from the distribution d. The standard deviation for each of these individual random variables would be given like this, as we talked about before. Now, if we let x bar n be the sample mean of this collection here, then the standard error of the sample mean will be given by this here, which is just the standard deviation of the x bar n. Alright, so let's look at a bit of an example. So the relationship between the standard deviation of the population, so we're talking about the population of an individual xi, and the standard error of the mean can be found through this following derivation. So we start with the standard error. We're going to square it just so that we don't have to carry around the square root. So it's defined to be the variance of the xn bars, And the xn bars are just the average value of the x's, so there's n of them, 1 over n, the sum of the x's. Now, when you have a constant, such as 1 over n, inside of the variance, you can pull that constant out as long as you square it. So we have 1 over n becomes 1 over n squared times the variance of the sum over the xi's, which is what we have right here. Now, because the xi's are independent, we can actually pull the summation out of the variance. So we have 1 over n squared, the sum of the variances of the xi's. Alright, and now we just have to notice that because these are all sampled from the same distribution, their variance is the same. So it actually doesn't matter what I is. I could be 1, 2, 3, n. They're all the same. So when we have the sum from 1 to n of something that does not depend on I, we just have n times that quantity. So we have 1 over n squared from before, and then n times the variance of any one of those random variables. Okay, just simplifying, the n cancels with one of the n's on the bottom. We have the variance of xi over n. And this is just sigma squared, or the standard deviation squared, divided by n. And square rooting both sides, we have the standard error is equal to the square root of sigma squared over n. Now, you need to remember that the standard error is the standard deviation of the mean. And this standard deviation here is a standard deviation of one of the variables, one of the random variables. Okay, and just to help you understand this with a visualization, here we have 3 different samples, one of size 5, one of size 10, and one of size 20. They're all sampled from the same distribution. So they're all sampled from a normal distribution with mean 0 and standard deviation 1. So you can see that we have 3 different lines on each of these. The red line is the standard deviation of the population, or the standard deviation of the distribution. These purple lines are the standard deviation of the sample. Now you can see that the standard deviation of the sample gets closer to the standard deviation of the population as n increases. This is what you'd expect, since the standard deviation of the sample is an approximation of the standard deviation of the population. And if n goes to the size of your population, then they should be equal to each other, because it's no longer an approximation, it's the actual value. Now, the blue bar is the standard error, which, as we showed previously, right here, is proportional to 1 over root n. So as n increases, going this way, the blue bars should get closer to 0. And you see that's what's happening here. Alright, I hope that you found this useful. Thank you for watching, and I'll see you guys next time.